All right, let's go ahead and get started. Last time we were introducing ourselves and covering sections, a little bit of 1.1 from WebWork, and really got you guys have the notes on 1.2. And I didn't quite finish 1.2 because it's kind of a large, like I said, review section and stuff. So I wanted to take a look at the last few problems from section 1.2 and then jump on into real calculus, which begins in section 1.3 dealing with the concept of limits. And if I'm real lucky, I'll have a few minutes at the end and I'll start tackling into section 1.4. So I'm going to flip over to our section 1.2 notes. We did pretty much most of it, but we stopped right there at the trigonometry section. And again, this is review, so a lot of my notes are going to be just basically reminding yourself of what exactly you need to know from previous math classes and stuff. So you'll notice that the goal here is basically review. Your job is to review sine, cosine, tangent, secant, cosecant, cotangent. You got your classic, remember, because this will be helpful later on, the classic sine graph. Remember, a sine graph starts at the origin, goes up, back down towards the minimum, then back to zero again. So this, you graph one period of a sine function. It starts at the origin, goes up, comes back down, and goes back up again. And then obviously it's periodic. It repeats itself. Cosine graph starts at the origin, starts at the top. At the origin, it starts at the top, which is at 1, comes back down, hits 0, goes down to the minimum at -1, comes back again to 0, and then hits the top again. Makes a little smiley face type thing right in here. And therefore, like I said, this is your classic sine graph, cosine graph, and it's periodic, so it just keeps repeating itself. Again, also on your Moodle site, I gave you guys a nice little handout of everything you're supposed to remember from your classic geometry and trig class. Another thing that everyone has had to have in here just to get into this class is exponential and logarithmic functions. Just to remind yourself what an exponential function is. An exponential function is a function that is a raised to the x, where a is some value, some number, a number raised to the x. The variable is in the exponent. That's called an exponential function. And it's called, like I said, if the base is greater than 1, it has what we call a growth graph. It horizontals out over here. If you go to negative infinity, hits 1 and then blows itself up. This is an exponential growth graph, is what your classic exponential graphs look like. The inverse of an exponential graph, again, quick review, reminding yourself, is the logarithmic graph. Y equals log base a of x. And that's how you would read it. But to be able to understand what y equals log base a of x is, you can always rewrite a log in terms of exponents because it's the inverse. It's b raised to the y value is equal to x. B raised to the y is equal to x. And if you'll notice, it's the exact opposite of y equals a to the x. You just switch the x and y. They're inverses of one another. So, a log graph is an inverse of an exponential graph. So if you draw the line y equals x-axis, they are symmetric to that line y equals x-axis. So this is your classic, in this case, log base 2 graph. You notice that you can't graph any. You cannot take the log of a negative number. You can't take the log of 0. It shoots straight down. Okay? And then it comes over and keeps on going slowly, but it keeps on going up forever and ever and ever. Again, this whole concept is a big review. And more reviewing of you guys from, like I said, your old college algebra days is transforms of functions. Something that you guys are going to have to kind of do on your own and some problems and stuff. And you got to know how to take a function and manipulate it. Very important in calculus. If I have a particular function and I add a constant to it, add a constant, what does that do to the function? It moves the graph up c units. Working outside the parenthesis moves it up or moves it down. If it's a minus c, it literally moves it down c units. That's called a vertical shift. If you have your constant inside the parenthesis where the x is at, it's called a horizontal shift. I have f of x minus c. The minus c is inside the parenthesis where the x is at. And I have f of x plus c. The c is being added inside where the x is at. But when you work inside the parentheses, it has this opposite effect. What I mean by that, you see that minus c right there? What effect does it have? You move it to the right c units. F of x is equal to x plus c. Inside the parentheses plus c, you think plus should be, remember it's going right or left, but plus, because it has that opposite effect, will be going to the left c units. A negative outside the function, negative f of x type thing here, a negative outside of a standard function does what to the graph? It reflects it about the x-axis. It flips it upside down in English. But a negative inside the parenthesis, just where the x is at, has the effect of reflecting, but it reflects it about the y-axis. Flips it around. And the last thing is vertical stretching and compressing. If you multiply a function times a constant, if that constant is greater than 1, it has a stretching effect. The graph is vertically stretched by a factor of c. So if I have like 2x squared, that would double the shape of the graph. It stretches out by a factor of 2. However, if c is a fraction, somewhere between 0 and 1, being a fraction, it's going to compress it and kind of shrink it down back towards the x-axis. The graph vertically shrinks by a factor of c. Again, the effects of adding and subtracting and multiplying constants and how that affects my graph. Again, a big review here. The next one is the combinations of functions. And the first type of combination function is something called a piecewise function. Again, we use these guys a lot in calculus. This idea of a function, but I have pieces that make up the entire function. So here's what a standard piecewise function looks like. F of x is equal to negative x plus 1 when x is less than 0. X when 0 is less than or equal to x, which is less than 2. And negative 1 when x is greater than 2. And what you do is you graph the pieces on one big coordinate axis. So x is less than 0. You're going to graph the line negative x plus 1, and there's my line negative x plus 1. Because you don't quite hit 0, you got to put an open circle there. Between 0 and 2, you actually hit 0, so that's a dot. So when I plug in, I get x. This is y equals x graph between 0 and 2. And at 0, we've put a filled-in dot because you hit 0. But at 2, it's an open circle because you don't hit 0. And negative 1 when x is greater than 2. X being greater than 2, you don't quite hit 2, so it's an open circle at 2. Negative 1, and for all other coordinates bigger than 2, you just get negative 1 throughout. And this is what we call a piecewise function. Also, we like to do combination of functions. And so, again, something that will be very helpful in calculus. If you have, this is the sum of two functions. If you're going to add them, you can call it that new functional notation. The f plus g of x. That means just take f of x and add it to g of x. F minus g of x, you've got f of x minus g of x. Just don't forget, when you're subtracting a function, don't forget to put parentheses around it, because that negative has a tendency to distribute. And without the parentheses, you've screwed up the whole problem. F times g, exactly what you're supposed to do. You take f of x times g of x, and f divided by g of x is f of x divided by g of x. And we're going to get back into this thing when we start talking about major rules of calculus, like product rules and quotient rules and the like. But all this is about that functional notation that you've been beaten to death with this stuff since about the 7th grade. All right, so for example, if I give you f of x is equal to x squared plus 5x plus 2, what would f of smiley face be? It's the whole concept behind what you learned in the 7th grade. I don't care what's inside that parentheses. Whatever is inside that parentheses gets to replace the what? X in the standard f of x notation. So this would be smiley face squared plus 5 smiley faces plus 2. All right, same idea here. G of x is 2x divided by the square root of x plus 1. What would g of 2 be? What are you supposed to do? Well, we're going to plug in 2 for all the x's. So it'll be a 2 there and a 2 there, and then clean it up. 2 times 2 is 4 divided by the square root of 3. Here's the beautiful part about calculus. We would accept this answer and you're good to go. Now, honestly, if you check the old back of the book, it would have a fit about this particular answer. Because if you remember your junior high and high school math class, it's really bad to have that square root in the denominator. You would have to rationalize the denominator. In calculus, we don't care. Leave it alone, circle it, great, we'll give you 100% credit on it. But in the back of the book, they would rationalize the square root of 3 by multiplying the top and bottom by square root of 3 and give you 4 square roots of 3 divided by 3. So remember, there's other alternatives to your answers. They're the same thing, it's just how it looks. But personally, I'm real happy with this, and so would anybody who teaches a calculus class. We're lovely on that. All right, now, k of x is equal to 2x minus 3. What would k of x plus h be? What am I supposed to do? You're supposed to take that x plus h and do what with it? Plug it in for every x. So that would just make, there was the x value right there. So replace x with x plus h. We're going to abuse this notation here. And if you wanted to clean them up, you would distribute the 2, and that would give you 2x plus 2h minus 3. And so in other words, if you got a function here, you can plug in numbers, and that gives you y coordinate values. You can plug in other values like x, and you can replace it with x plus h. You can also replace x with an entirely different function. Take a look at this next guy. I got h of x being equal to the square root of x squared plus 5x. What would h of k of x be, given that k of x is up here? What would it be? Well, replacing all the x's with k of x, here was an x, and here's an x. So I'll replace that x with k of x. But k of x is 2x minus 3, so 2x minus 3 would go here. And officially I'm supposed to put it down here. 2x minus 3 goes here, and 2x minus 3 goes here, because wherever the x's are, that's what you're supposed to plug in k of x at. So k of x goes here, and k of x goes here, and you replace your k of x with what it's equal to. So this would be what my answer is. Composition of functions. But there's lots of different ways to do composition of functions. So these guys are on your web work. So I thought I'd throw a couple of them before we move on to section 1.3. For functions, f of x equals square root of x and g of x equals x plus 2. Find f of g of x. See that little circle there? That's composition. This means f of g of x. How you do this particular problem is this. You got to look at it from an outside-inside perspective. Again, this concept is going to haunt you back in calculus again. Outside-inside perspective. What's on the outside? What function's on the outside? F. What does f look like? Square root. So square root of x, but leave a blank for the x. What inside replaces the x. The inside is the g of x function. What's g of x function? X plus 2. So I'm replacing the x with x plus 2 in the f function, which was the square root of x. So you get the square root of x plus 2. That is my answer. Does that make sense? But if you can fog this guy, you can also golf this guy. G of f of x. This is g of f of x. But now who's your commander? Who's the guy on the outside? G. G looks like somebody plus 2. That's the g function. And on the inside goes the f, and the f is the square root of x. So the answer is the square root of x plus 2. And you can also do things like numbers. This would be f of g of 2. Or this would be f of g of, the g function was x plus 2. So this would be x plus 2. And replacing the x with 2. And you can clean this guy up. What's 2 plus 2? 4. So I'm working the inside first. So I cleaned it up on the inside. That's g of 2 is equal to 4. So this is f of 4. And what's f equal to? That's the square root. And the square root of 4 is 2. So the answer is 2. And you don't forget, you can do golfs and fogs, but you can also do gogs. G of x. What does that mean? G's on the outside and G's on the inside. You're plugging G into the x of the g function. Who's your commander? The guy on the outside. What does G look like? Somebody plus 2. What goes in the x on the inside? Another x plus 2. And if you clean it up, you get the answer x plus 4. Does that make sense? Questions? But that notation comes back, and they love to give this kind of problem on final exams as well as web work. So, here we go. This one, they didn't give you a function. What they gave you is a graph of the function. So it's trying to tie in the visual perspective, the graph of the function, with this composition notation. what am I supposed to find here? F of g of 2. That is f of g of 2. When you're working the graphs, you're trying to calculate what value this guy's going to be. You want to work on the inside first. This would be f of, what's g of 2? Well, you look on your graph and go, okay, here's my g function. Here's the origin. G of 2, the x coordinate is 2, so that's 1, 2. What would my g coordinate be? G, remember, is your functional coordinate of the g graph, which is 1, 2, 3, 4, what is it? 5. So f of g of 2 is the same thing as f of 5, because g of 2 equals 5. And now you just got to go find what f of 5 is. Here's my f function. The x coordinate now is 5. Here's 0, 1, 2, 3, 4, 5. There's 5. And remember, the functional value is the y coordinate, so let's figure out the y at 5. 1, 2, 3, 4. So the answer is 4. Does that make sense? All right? Let's try this one. What would g of f of 2 be? This is g of f of 2. This is g of, what would f of 2 be? All right, well, here's 2, 1, 2. F, that's the light little function here. It'll be 1, 2, but it's negative. That would be negative 2. And then g of negative 2, here's 0, here's negative 1, here's negative 2. G is back to 1, 2. So the answer is 2. Does that make sense? And I'm not doing them all for you guys. You can do these. I just want to show you because this is definitely on WebWork. F of 4. So I'm going to do f of 4. Work inside the parentheses first. What's f of 4? Here's 0, 1, 2, 3, 4. What's f of that? 1, 2. It's 2, so that'll be f of 2. F of 4 is equal to 2. Now I'm supposed to calculate f of 2. When x is 2, the y coordinate for f function would be 0, 0, negative 1, negative 2. It would be negative 2. Does that make sense? It's not hard once you know what you're doing, but it's nice for me to do a problem like this because if you actually were given this right from the get-go, a lot of people would be just lost on what to do because they've never seen anything like this before. You're supposed to use the graph to be able to calculate what the values are. That's the big deal. Okay? Well, there's your big review section from 1.2 that I wanted to finish up here.